Hey ANPers, this is Dr. Jones checking in. This is ANP1 Lecture Test 5 video. I think we're on video 11 for page 13, maybe? Yeah, I think so. Okay, so the first thing is to draw this picture. So, we can do that. So we're going to start here at negative 70 millivolts. And then we're going to apply our stimulus, and that makes the inside of the cell less negative, which is depolarization. And then once we remove the stimulus, it goes back down to resting membrane potential. And the process of going back down, going back more negative, is repolarization. And then what happens, so these are graded potentials. This happens if you open chemical stimulus that opens sodium ion channels. I put the plus that tells you that it's an ion. Green doesn't show on that background, does it? Let's do the blue. Okay. So I think the green would have shown on this color. So if you open sodium ion channels, you get a depolarization. It makes it less negative because sodium, like fools, rush in. Anytime you increase sodium permeability, sodium rushes inside the cell. And since the inside of the cell is relatively negative, when you add a bunch of positive to that negative space, it's less negative. Like the whole group says, we're never going to make it through this semester. We're all going to die of stress. And one person says, I think we can do it. It's still negative, but it's less negative. And I'm that person. I think you can do it. So then when you shut that ion channel and that chemical stimulus is removed, it goes back down to resting, which is repolarization. So you're going back to polarized. Polarized being the negative 70. Way up here would be 0. 0 is neutral. So if there's no difference between the inside and the outside of the membrane, then it would be 0. It would be neutral. But we're polarized. We're negative on the inside, positive on the outside. That's the polarized. So when the sodium ions rush in, it's less negative, less polarized. So that's depolarization. And then when it goes back to resting, which is negative 70 millivolts, that's repolarization, taking it back to polarized. Okay. So what if you use a chemical stimulus that opens a potassium ion channel? Well, when you open a potassium ion channel and increase your potassium permeability, potassium ions rush out of the cell. Now, they are also positive ions. So the inside of the cell is negative and we're losing positive ions. So which direction is that going to go? Is that going to go depolarized again? It's going to be more negative. So this is when you owe $70 on your Kohl's card and you go and you put another $10 shirt on the card. You are hyperpolarizing. You are now in even more debt because you have lost you've lost. Although you've got a great $10 Kohl's shirt, so. But you have hyperpolarized, you're more in debt. Your balance is more negative than it was before. And then this depolarization, undoing the depolarization is repolarization. Hyperpolarization is more negative. And then we don't have a neat term for going back to normal. We call it return to resting membrane potential. Totally need a 50-cent word for that, right? Like, need a word. Depolarization, undoing the depolarization is repolarization. Opposite direction is hyperpolarization. Redepolarization. Yeah, no. I don't know what that term should be, but there should be a term. Totally. Okay. All right, so if you open a potassium ion channel, the inside is going to get more negative. It's going to, zero still up here. So with depolarization, you get physically closer to zero, normal. Repolarization is back to normal. But if you open a potassium ion channel, you get hyperpolarization where you're physically further from neutral. You're further from zero. Now you're at -80 instead of you're resting -70. So pay down your Kohl's card. All your credit cards. Pay off your credit cards. Okay, so repolarization, back to the note set, you can draw all of that there. And the main reason I wanted you to draw this is because I want you to know that graded potentials, we need another color for this. Oh, and we are totally going magenta. We're going to make a point. We're going to do it in magenta. Graded potentials can be either depolarizing or hyperpolarizing. Mic drop. That's how that works. So repolarization is when you return to resting membrane potential after a depolarization. Opening, chemically gated sodium ion channels allow positively charged sodium ions into the cell, causing, did you say depolarization? Say depolarization. No, actually, I want you to say these words out loud because saying them out loud is more interactive than just thinking them in your head. So, like, if we were in-person class, I have been known to make everybody say the word over and over until I see every single mouth in the room move at the same time. Because when you say it out loud, that helps you remember it better, more than just listening to it or just thinking about it or just reading it. Writing it helps you remember it. That's why I made a fill-in-the-blank note set to make y'all write it down. And in class, I keep asking these questions and leaving blanks in the videos so that you can answer. And I really, literally, but in the actual meaning of the word literally, really literally actually intend for you to say all of these words out loud. So that's why I will often give you the answer and then ask the question to give you a chance to come up with the answer in your head, say it out loud, and then compare it with what I said. Is it the same thing but said in a different way? Is it the same, you know what I mean? Are there different terms for the same thing, like synaptic, terminal, axon, terminal, synaptic knob are all three the same thing? You know, if I say one and you said one of the other two, then we've still said the same thing. Okay. It's better to answer wrong and learn than to not answer. Third blank, so you know I'm serious. Okay. We're on this page of Noteset. I think we did sodium channels. So opening chemically gated potassium channels allows positively charged potassium ions, K+, out of the cell, causing hyperpolarization. I've been seeing this thing around with like stars, and they have a star and it's like 1, 2, 3, 4, 5. And they're like, well, which do you draw it? And they like number all 5 of them. And I'm like, I'm a 5 too. Like I start at 5 and then I go to 2. And if if you can't figure out where I go from there, then I'm not going to tell you. I don't have to remember all 5. It's quite clear once you've got the first 2 which direction you're going. And I seem to be the only person that does that. And they asked me if I was a lefty. Like, no, it's just I thought you were supposed to write from left to right. Plus, this line is like parallel, and I can't judge angles. So if I start with a parallel line, then at least I've got one right. Hashtag not an artist. All right, that was off topic. Oh, I made a star. Yeah, sorry about that. Oh, look, it's the picture on the test. We should learn about that. We'll draw it on the next page. Top of the next page. Oh, middle of the next page. Fun, fun. Okay. An action potential. Action potential is, and I quote from the book, a propagated change in the transmembrane potential that affects the entire excitable membrane. Again, a propagated change in the transmembrane potential that affects the entire excitable membrane. And a nerve impulse is just another word for the action potential. It's an electrical event, and it propagates, which means sweeps down the entire length of the axolemma, and we will talk about how later, not today. Well, not in this video anyway, maybe today. Not sure. As I record this, I've lost my daylight savings time, and so it gets dark really early now. I used to be able to still record videos at like 7:30, 8, and still have a little light out the window over here, but okay. Okay, so threshold. Threshold is the was there another slide we're supposed to be looking at? Nope. Okay. Threshold is the transmembrane potential at which an action potential begins, and that is negative 60 millivolts, which I covered more than I circled, so I'll write it down, millivolts. If the initial segment is depolarized to threshold, it starts an action potential, and just so you know, that is highlighted in my note set. Dun, dun, dun. Okay, so memorize the High Holy Hades out of that. What happens if the initial segment is depolarized, but like to less than threshold? Nothing. Nada. Absolutely. Zip, zilch, zero. Nothing happens. How is a graded potential like shooting with a bow and arrow, while an action potential is like shooting with a gun? And the answer is threshold. That's the difference. So when you shoot with a bow and arrow, let's see if I can get it on screen here, you can put like a little draw pressure into it and the arrow just, it won't go very far. Or if you're big and strong and you actually can draw the bow, you put a lot of pressure in it, however the arrows go, there we go, up by your face, and let it go, and you get more distance on the arrow. So when you change the input, you change the output, and that's like a graded potential, where we said if you add more acetylcholine to the system, you open more of those chemically gated ion channels and get that much more sodium into the cell, which is like throwing a bigger rock into the pond and getting bigger ripples. So the effect is stronger and it'll go out a little further. Action potential is like shooting a gun, where, trigger discipline, not ready, okay now. Where if you squeeze just a little but you haven't met the trigger pull, absolutely trigger discipline. Absolutely nothing happens because you haven't squeezed enough, pulled, squeezed? You haven't put enough pressure into the system to make anything happen yet. Now, if you squeeze enough to meet the trigger pull and the gun shoots, if you squeezed it twice as hard, would that make the bullet go twice as far? No. Once you've met threshold, once you've met the trigger pull, then the bullet goes on the trajectory it goes on based on that gun and which ammo you're shooting. Okay, it has nothing to do with how hard you've squeezed the trigger after you meet the trigger pull. Same with the action potential. Once you have, let me get back in screen here, once you have met the threshold, the action potential goes, and it goes the exact same every time because there's not different guns and there's not different ammo here. It's just you get the action potential goes. And it's the exact same every time. But if you haven't met threshold, you haven't done anything. You're not making a tiny ripple in the pond. There's like literally nothing is happening. You haven't thrown the rock. Nothing has happened. Okay. So that's how a graded potential is like shooting with a bow and arrow, while an action potential is like shooting with a gun. Threshold. Excuse me. All right, so also highlighted in my note set. If, bottom of the page, if graded potentials created by chemically gated ion channels depolarize the initial segment to threshold, the depolarization itself triggers voltage-gated ion channels to start an action potential. I didn't mean to throw a true-false on that. That is a summary, that is a basic need-to-know concept. Let me draw you that. Let me draw that for you. Okay, so we have a neuron. Okay, here's our axon, soma. They call that the cell body now, don't they? The dendrites receive information. Okay, sum up. The soma and the dendrites have chemically gated ion channels. So a different neuron somewhere else is synapsing with our red neuron. So our red neuron is the postsynaptic cell. The blue neuron is the presynaptic cell. And the synaptic cleft will be the gap that I did not draw between the synaptic knobs of the blue neuron and the soma and dendrites of the red neuron. Give you a second for that to sink in. Okay, so when this first cell, the blue cell, makes an action potential, it propagates down the axon, causes the release into the synaptic cleft, which affects the postsynaptic membrane. These are like rocks in the pond, creating ripples that are stronger, closer, and get weaker as they go out. Okay, so at the axon hillock, which on the model was orange. I don't have orange. Okay. Axon hillock. So the effects of these graded potential on the axon hillock determine whether or not we bring the initial segment. Now I'm trying to draw it right small so it gets more difficult. Initial segment. Be easier to write in cursive. Okay. Whether or not the axon, all right, let's do this again. So let's make a green neuron. That was terrible. We'll go with this. So say the green neuron is able to bring the axon hillock from resting, what's resting? Negative 70 millivolts. Say these are strong enough and close enough and repeated over time, which we'll discuss later, to bring the axon hillock to threshold, negative 60 millivolts. The negative 60 millivolts at the axon hillock brings the initial segment to threshold, starts the action potential in the postsynaptic cell, which gets propagated down to the end and causes the release of a neurotransmitter into these synaptic clefts at the ends of these synaptic knobs. There's another cell here, or 5, I don't know. Now that we've drawn all that, let's go back to our summary at the bottom of the page. If the graded potentials created by chemically gated ion channels, so that's from the blue cell and the green cell, depolarize the initial segment to threshold, the depolarization itself triggers the voltage-gated ion channels to start an action potential. So that's why we say that the axon hillock is the location of the information processing, because it's at the axon hillock that we determine if the signal is strong enough to be repeated to the next cell. All right, that's enough for one video. This has been ANP1 Lecture Test 5, Video 11, covering page 13. On our next video, we will draw the action potential, which is the picture on the test. Thank you, as always, for tuning in. The education must go on. Dr. J out.